Good morning, everyone. Hope that you're having a great start to the day. The unit that we're currently in is called Rational Functions and Function Operations. And we've just finished Chapter 9, which deals with rational functions. You wrote that quiz this morning in our seminar, and I will have that marked and back to you tomorrow. But the other part of this unit deals with what's in Chapter 10, and Chapter 10 deals with what we call function operations. Function operations are simply taking two different functions of x, usually, and performing operations on them. So if you add two functions together, or you subtract two functions, or you multiply two functions, or you divide two functions, you're performing function operations. So you should be looking at page 10 of your unit handout. We've got three basic objectives today, and the idea behind all of this is fairly simple. We want to be able to sketch the graph of a function that is the sum of two other functions, or to sketch the difference of two other functions as a new function. We want to be able to determine the domain and range of the sum of two functions, or the domain and range of the difference of two functions. And finally, we have to be able to write the equation of a function that is the sum of two functions, or the equation of a function that is the difference of two functions. To begin with, we have kind of definitions that we have to talk about here. It's more about notation than an actual definition, but we call them definitions in mathematics. The sum of two functions can be written as f plus g of x, and what that means is f of x plus g of x. When I say f plus g of x, I believe that pause in between me saying f plus g and me saying x is important. Because if you just say f plus g of x, you might mistakenly think that you're talking about this, and that's not what you're talking about. Often when we pronounce f plus g of x, we add in a little bit extra just to drive the meaning home. And that little bit extra is to say f plus g quantity of x. Regardless, f plus g of x simply means f of x plus g of x. And if you're like me, if that's what it means in simplest form, why do we need to complicate things and write it in a different way? And the answer to that question is because that first notation, f plus g, quantity of x, is very useful, and in fact it's the only notation that's going to take us through some math problems, whereas f of x plus g of x just doesn't help us at all. The other definition is that the difference of two functions can be written as f minus g of x, and what that means is f of x minus g of x. I want to point something out to you, and you can try this with numbers, that if you take two different numbers, and you add them together, it doesn't matter the order in which you add them. So for example, 11 plus 7 is 18. If I decide instead of saying 11 plus 7, I say 7 plus 11, I still get 18. And that means that whenever you add quantities together, the order doesn't matter. And what that means is that f of x plus g of x and g of x plus f of x are the same thing. So when you see f plus g, quantity of x, you can choose to interpret that as f of x plus g of x, or you can interpret that as g of x plus f of x, and you're not going to go wrong. One person interprets it one way, you're sitting next to them, you interpret it a different way, you're going to get the same result. The math is the same no matter what. But going back to our numbers of 11 and 7, if I said to you, what is 11 minus 7? 11 minus 7 is 4. If I said to you, what is 7 minus 11, 7 minus 11 is not 4, it's negative 4, which means that f of x minus g of x is not equal to g of x minus f of x. And what that means is anytime that you see f minus g of x, there is one and only one way to interpret that, and it's to interpret it as f of x minus g of x. You cannot interpret it as g of x minus f of x. In other words, when you subtract, order changes the result. When you add, order of addition does not change the result. So we're going to start off with an example where we're given two functions, f of x equals 2x plus 1 and g of x equals x squared. This is a very basic linear function which you hopefully know how to graph, and this is the simplest quadratic function in the universe, which again you should be familiar with in terms of its graph. The third function is going to be h of x. So you're asked to determine the equation of the function h of x if h of x is equal to f plus g of x. Well, that means that h of x is equal to f of x plus g of x. Based on our definition, f plus g, quantity of x, equals f of x plus g of x. Now, this is really simple, this first part of the example. F of x is 2x plus 1. G of x is x squared. So if you're asked to determine h of x and it's the sum of f of x and g of x, then I guess h of x is going to be 2x plus 1, which is f of x, plus x squared, which is g of x. We would probably write that in descending order of degree, quadratic term, then the linear term, then the constant term. So there's the equation of the sum of the two functions. Now we are asked to sketch the graphs of all three of these functions. You're asked to sketch the graph of f of x equals 2x plus 1, g of x equals x squared, and h of x equals, well, x squared plus 2x plus 1. I've got a table of values here that we're going to use not to build the sketches of the graphs, but to learn what the relationship is between two functions being added together and the resulting third function. If I were to use the table of values when x is negative 2 in the first column, and I put negative 2 in for x here, I'm going to have 2 times negative 2, which is negative 4, plus 1, which gives me negative 3. If I were to put negative 1 in for x here, I would have 2 times negative 1, which is negative 2, plus 1, which is negative 1. And I could continue on this little journey. What I would discover, by the way, is that every time x increases by 1, y increases by 2, because the slope of this linear function is 2. Speaking of y coordinates, I want to make it crystal clear here that this column is the y coordinate on f of x, which means 2 comma negative 3 is a point on the function. Negative 1 comma negative 1 is a point on the function. 2 comma 5 is a point on the function. Let's fill in the second column, and again we're doing this, I guess, so that we understand the relationship between the three functions. We're not really doing this so that we can see what the graphs look like. We know what some of these graphs look like. So I take x equals negative 2 and I put negative 2 in here, and when I square negative 2 I get 4. Then I put negative 1 in, so I'm always going back to the first column to find out what my x coordinate is. I put negative 1 in, I square it, I get 1. I put 0 in, I get 0. 1 squared is 1 again, 2 squared is 4. And I want to point out to you that this column is the y coordinate on g of x. And now if I said to you complete h of x, what we could do is put -2 in here and calculate what that number is going to give us. We would take -2 quantity squared, we would add 2 multiplied by -2, and then we would add 1. But I don't need to do that. I know that this will give me 1, and the reason is, it's kind of complicated until you see it. This third column is the y coordinate on h of x, but look at how we calculate the y coordinate on h of x. We're going to take 2x plus 1 and we're going to add x squared, which means if you look at the top of this table where I've written y coordinate on f of x, y coordinate on g of x, y coordinate on h of x, the y coordinate on h of x is the sum of the y coordinates on f of x and g of x. And this is really the lesson. We can simply add the individual y coordinates together to get the y coordinate on the new function, which is the sum of the two functions. This is crucial in this lesson, that you're understanding when you add two functions together, you're simply adding the y coordinates together. And after all, when we see f of x, when you're first taught about function notation, I believe back in grade 10, your teacher probably, and I know I do, tell you initially, don't worry about it. When you see f of x, just think of it as y. And then our understanding of function notation becomes more sophisticated and complicated, and we have different functions, f of x, g of x, h of x. Because f of x is y, but it's the y coordinate on that first function. G of x is y, but it's the y coordinate on the second function. H of x is y, but it's the y coordinate on the third function. So now let's talk about sketching these. And I'm not going to use the table of values. I'm just going to talk to begin with here about y equals 2x plus 1. You should know what this graph looks like. This graph has a slope equal to 2 and a y-intercept equal to 1. So if I plot a point at 1, and then from there I use the concept of slope being rise over run, if the slope is 2, that means we can think of the slope as 2 over 1, and that means that the run is equal to 1 and the rise is 2. All that means is from our y-intercept you go 1 to the right and 2 up, 1 to the right and 2 up, 1 to the right and 2 up. And you continue this and we can go in the opposite direction thinking backwards as well. I'm going to teach this a little bit different than I normally would teach it. I'm not going to ask you to draw a straight line through those points because that is not the point of this example. You could put a ruler down and draw it. It doesn't really matter. But that function is y equals 2x plus 1. And again, you could draw a straight line, but I really don't want you to. What about the next function, which is y is equal to x squared, which I'll do in green? Well, you don't need a table of values for that. You should know that x squared has a vertex at the origin. It's a parabola that opens up. And since it's x squared, every time you go 1 to the left or the right of the vertex, you're going to go 1 up because -1 squared is 1, +1 squared is 1. Every time you go 2 to the right, then you're going to go up 4. That's the nature of it being x squared. It's quadratic because -2 squared is 4 and +2 squared is 4. If I go 3 to the right and I square that, I get 9. Similarly on the left. So, well, so what? So what's the point of all this? You could draw a curve through these green points as well, but that's y equals x squared. The point is that the sum of the two functions is x squared, which is the y-coordinate on the green function, plus 2x plus 1, which is the y-coordinate on the brown function. So we simply have to look in different places on the graph and add the two y-coordinates to get the sum of the two functions. For example, if I take a look at x equals 0, so I'm looking along this line pointing up at x equals 0. I see the y-coordinate of the green function is 0. The y-coordinate of the brown function is 1. We add those two numbers together because this is the y-coordinate of the green function and this is the y-coordinate of the brown function. So we add those two numbers together. 0 plus 1 gives 1. And that means that those 2 points conspire to produce this point, which I'm just going to make a little bit smaller so that you can see that it's not, well, so that you can see there's still another point underneath it. Then I could go to x equals 1. And now I'm going to look at the y-coordinate on the brown graph and the y-coordinate on the green graph. And I see that we have y-coordinates of 1 and 3. When I add those two together, 1 plus 3 is 4. If there was ever a time for what I've asked you to do before, which is to be very careful, thoughtful, and deliberate in your work, now is the time. This isn't algebra, but there's a lot to keep track of. Let's go back to -1. So I'm looking over here at -1. And the brown graph has a y-coordinate here, and the green graph has a y-coordinate here. Visually, this is difficult. The y-coordinate of the brown graph is -1. The y-coordinate of the green graph is +1. When I add those two numbers together, 1 plus -1, I get 0. Let's go over to +2 now. I'll turn my arrows around so that it's a little easier to talk about. At +2, the brown graph is at 5 for a y-coordinate, whereas the green graph is at 4. 5 plus 4 is 9. So at -2, the y-coordinate will be 9. And you're starting to see that we are getting, this graph I will kind of sketch. I'm focusing on the red points, and I am getting a parabola. Went a little bit off the rails there near the end. Do that again. I am getting a parabola. There's half of the parabola, and we could continue in the other direction. If I go to -2 for x, we have a y-coordinate on the brown function of -3. We have a y-coordinate on the green function way up here at 4. -3 plus 4 is 1. So at -2, these two y-coordinates get together to produce a y-coordinate of 1. So, quite frankly, I don't care about the sketches of the graphs. What I care about is the lesson that basically, when you take on f of x a point, and you take at the same value of x on g of x a point, these 2 points marry to produce that same x coordinate with the sum of the y coordinates. This is what happens when you add 2 functions together. This form of mapping that you're looking at is something that I made up. I've never seen it in a textbook, so I don't know Well, I would say, you know what, if you put that on a diploma exam on a written response, I would hope the marker would look at it and go, yeah, this student knows what they're talking about. So let's finish this example. What's the domain and range of h of x? Well, you can take a look at the graph. It's a parabola which extends to the left and the right forever, which means the domain is any real number for x. And this parabola happens to have its vertex on the x-axis. So that means that the range is y is equal to 0 or greater than 0. What are the values of f of 4, g of 4, and h of 4? I'm going to give everybody a minute here to put 4 in for x into each of those three functions to calculate the three y coordinates. When you put 4 in for x and f of x, you get 2 times 4 plus 1, which is 9. When you put 4 in for x in g of x, you get 4 squared, which is 16. And if you were to put 4 in for x in h of x, you would get 4 squared plus 2 times 4 plus 1. And if you figured out what that is, you're going to get 25. But if you've learned the lesson already, of course you get 25 because 9 plus 16 gives you 25. So again, what this is telling you is that 4 comma 9 is on f. This is telling you that 4 comma 16 is on g. And this is telling you that 4 comma 25 is on h. So there you have that idea that the x coordinate stays the same and you're adding the y coordinates. So how are the y coordinates of the points on the graph of h of x related to those on the graphs of f of x and g of x? Very succinctly, the y coordinate on f of x plus the y coordinate on g of x must give you the y coordinate on h of x. I'm going to add one little detail here for a particular x coordinate. Right, you have to be looking at, say, x equals 5. And then you focus on x equals 5 and you look at the y coordinates and you add them. Number 2, consider the functions root x minus 1 as f of x and g of x equals x minus 2. These are both functions. I'm going to go a little bit out of order here, but these are both functions that you know the appearance of graphically. We have a linear function x minus 2, which it doesn't get much simpler than that for a graph or a function at this level. And then we have the radical function f of x equals root x minus 1, which it's a little complicated, but we learned about that in chapter 2, I believe, of this course. I'm going to jump to the graph before we even do the equation or talk about tables of values. I'm going to talk about the graphs of these functions. So if I pick, the colors don't really matter. I'm going to pick y equals x minus 2 as the brown graph. That has a y-intercept of -2 and a slope of 1. So this is going to be the series of points that we could use to construct a line graph for y equals x minus 2. I shouldn't say line graph, the graph of the linear function. Now, do you know what y equals root x minus 1 looks like? Well, I don't want to muddy up this graph, but just to show you that you do know what it looks like. You learned in chapter 2 that y equals root x goes through the origin, goes through 1, 1, goes through 2, 4, goes through 3, 9. You learned what this looks like. It's the basic square root function. And that would mean that y equals root x minus 1 is this graph shifted 1 to the right. And we could certainly use the table of values. I'll be honest with you, I don't even think we're going to touch the table of values as I finish this example. So I can plot the points on root x minus 1. Its vertex will be at 1. You go up 1 and over 1. You go up 2 and over 4. I'm just going to make that a little smaller so you can see there's a common point there. You go up 3 and over 9, and I would say that's the best we can do. Now I'm going to refer, I take it back, I'm going to refer to the table of values a little bit in a minute, but those are the two graphs, and if you had a steady artistic hand, you could certainly sketch root x, and you could certainly sketch x minus 2. You don't have to, and in fact, I'm not sure I want you to. Your call. What is the equation of f minus g of x? Well, that new function means f of x minus g of x, which means h of x is equal to root x minus 1 minus x minus 2. And I would probably say it would be better to write it as root x minus 1 minus x plus 2, because we can distribute that negative into the binomial and not have to worry about a set of brackets. So just in the square brackets, I have an alternate way of writing that. If you look at the table of values, I'm not going to fill it in. I'm just going to point out that this is the y-coordinate on f, this is the y-coordinate on g, and this is the y-coordinate on h. And you can see that the y-coordinate on h is root x minus 1 minus the x minus 2, which is the same as what's written above there. And again, I'm really hoping that you're picking up on this because it's the main point of this lesson. This is the y-coordinate on f. This is the y-coordinate on g. So really, what you're saying is the y-coordinate on h is the y-coordinate on f minus the y-coordinate on g. We don't need to fill in the table of values. We need to go, and this will be done very carefully, we need to go to our graph and start subtracting y-coordinates. But because subtraction is an order-sensitive operation, we have to be very careful here. So I will do the difference of these two functions in red. If I were to look at, say, x equals 6, and I look at the y-coordinate on the green graph and the y-coordinate on the brown graph, the y-coordinate on the brown graph is not approximately, it's exactly 4. The y-coordinate on the green graph looks to be about 2.5. We have to, for h of x, take root x minus 1 minus the x minus 2. So we have to take the green minus the brown. We have to subtract them in that particular order. So I need to take 2.5 minus 4, which gives me negative 1.5. So these 2 points, this point and the brown point above it, are going to turn into, at the same x coordinate, are going to turn into negative 1.5, 2.5 minus 4. We move over to 5. There's a very methodical way to do this. We take a look here at the y coordinate on the green function. And the y coordinate on the brown function. The y coordinate on the green function is I'm going to say 2.2. The y coordinate on the brown function is 3. You certainly don't need to write these numbers down. I'm putting them on the screen to explain what it is I'm doing. Now we take 2.2 minus 3 and you get negative 0.8. So these 2 points, this green point and this brown point, become negative 0.8. Take a look here. I'm not going to draw the locations of those. The two y coordinates of that intersection point are pretty much equal. Not pretty much, they are equal. So when I subtract the green y coordinate minus the brown y coordinate, I'm going to get 0. It's tedious, I know. When I go over here, I'm going to stop writing down the numbers. The y coordinate on the green function here, I would say is about 1.5, minus the y coordinate on the brown, which is 1, gives us 1.5 minus 1, which is about 0.5. When I go here, I'm going to take the y coordinate on the green minus the y coordinate on the brown. That will be 1 minus 0, which is still 1. I'll just make it a little smaller so you can see there is a green point there. When I go over here to 1, I'm going to take the y coordinate on the green, which is 0, minus the y coordinate on the brown, which is negative 1. 0 minus negative 1 is 1. I'm not too concerned about this next bit of business, but if you were to look in this region, what you would discover is that the graph will end up having a little tiny bump above y equals 1, and then it curves down. So that's what the function would look like. Now hang on a second here. Why did I stop there? This next bit of business is important. If I tell you, let's go over to 0, to x equals 0, and we're going to take the y coordinate on the green minus the y coordinate on the brown, you can't do it. In other words, everyone, the only way the difference or the sum of two functions exists is if the two functions exist. Over in this region, in this general region here, the square root of x minus 1 doesn't exist. So if it doesn't exist, there are no y coordinates that you can subtract the other y coordinates from. So that's what the graph looks like. Again, don't get hung up on the graphs. Get hung up on the fact that we're subtracting y coordinates. Let's answer the rest of the question. What is the domain of h of x? Well, x is greater than or equal to 1. We can take a look at the graph. In tomorrow's lesson, where we'll have a little more time, we're looking at the red graph here, so you can see x is greater than or equal to 1. Tomorrow, when we have a little more time, I'm going to introduce you to something called the domain rule. There's a reason why the domain of h of x is what it is. And we'll get to that tomorrow. What is the range? Well, notice it says use the graph to approximate the range. And when you take a look at the graph, this graph is peaking a little bit above 1. And I don't, quite frankly, think it's worth our time or effort to graph this on a graphing calculator and find the exact coordinates. I'm just going to say, based on what I've drawn, that the range is y is less than or equal to 1.2. And I don't know if I've ever seen this before. I'm going to put a dot over the inequality symbol. That just means it's approximate. I don't know exactly what it is. If you're going to go on and take calculus next semester, there's certainly some things we could do to find algebraically the y coordinate of that maximum point. Just looking at the clock right now, so we've gone through about 35-40 minutes here of recording. This is going according to plan, I think. You're going to have lots of time here to work on your stuff. How are the y coordinates of the points on the graph of h of x related to the y coordinates on the graphs of f of x and g of x? Well, the y coordinate on h of x can be found by taking the y coordinate on f and subtracting the y coordinate on g. It has to be done in that order because h of x was f minus g of x. So you have to subtract f minus g. You can't subtract the other way around. The unfortunate thing about doing this with video is at this point I would probably ask you, does anybody have any questions? And I'm sure some of you might have questions for clarification. But you're going to have to wait to get your questions addressed. You'll have to wait for tomorrow. We have one last example to do. I'm sure it occurred to some of you that we could have done examples 1 and 2 with the graphing calculator, but you cannot do example 3 with the graphing calculator. You're given the graphs of f of x and g of x in question 3, and you were asked to sketch the graph of f plus g of x. Now, I just want to make sure you understand what you're looking at on the screen. The two graphs on the right are f of x and g of x. I've just put them there so that I can refer to them. You don't need to redraw them. You can certainly refer to them by just looking up at the top where it says example 3. So I'm going to ask a question that I think is important. Can I start talking about, give me a second to format something. Can I start talking about this location on these two graphs? That is to say, can I start adding the y coordinates? Because that's what I'm supposed to be doing. Y equals f plus g of x means y equals f of x plus g of x, which means I add the y coordinates. So can I add the y coordinates of these two functions where x is -1? No. Neither function exists there. Neither function exists until we get to x equals 1. That's where they first spring into existence. And the y coordinate of f is 2 and the y coordinate of g is 0. So we're adding y coordinates. 0 plus 2 is 2. And that means when x is 1, y equals 2 will be where the point is for the sum of the two functions. We can go over now to x equals 2. And again, this is all kind of scrap paper work, or it's mental work going on in your brain. This y coordinate at 2 is 3. This y coordinate at 2 is 1. 3 plus 1 is 4. So when x is 2, y is 4. We can move over to x equals 3, and we just keep repeating the process, everybody. We've got a y coordinate of 4, a y coordinate of 2. We add those two numbers together because we're finding the sum of two functions. We get 6. So when x is 3, y is 6. We can keep going because there are more places where these two functions both exist. Another place is where x equals 4. And on the top function, on my view, on f, y is 4. And on g, y is 1. So we take 4 plus 1, and we get 5. We've got one more point where we can add the y coordinates, or one more location, I should say. We're looking at this, which is y equals 4. We're looking at this, which is y equals 0. 4 plus 0 is 4, so we get this function. And this is what the sum of the two functions looks like. Try one final example, and I wish I were here in the room with you so I could find out if you're picking up my drift here. Y equals f minus g quantity of x means y equals f of x minus g of x. What does that mean? It means that we're going to take the y coordinate of f and subtract the y coordinate of g. So again, we can go to x equals 1 as a starting point, and we're going to look at the two y coordinates. We have 2 for f and 0 for g. We're taking f minus g, so you take 2 minus 0 and you get 2. When x is 1, y is 2. We can move on to x equals 2. Now we're focusing on this point and this point. Y coordinate is 3 for f, y coordinate is 1 for g, 3 minus 1 is 2. Well, that's interesting. I think it is anyway. We get the same y coordinate for the difference. And many of you will understand that in this region, from 1 to 3, the difference is going to be the same everywhere because those two lines have equal slopes. So one of the lines is always 2 above the other line. For example, when you go to 3, and it is tedious, I understand that. The y coordinate is 4, the y coordinate is 2, 4 minus 2 is 2. So this region of the graph will be a plateau with a slope of 0. We move on to 4. I'm not going to write these numbers down. The y coordinate on the top is 4, minus the y coordinate on the bottom is 1. 4 minus 1 is 3. So at x equals 4, y is 3. We move on to x equals 5. The y coordinate of f is 4, minus the y coordinate of g, which would be 0. 4 minus 0 is 4. So that is what f minus g of x looks like. By my count, this video will end up being about 40 minutes long, which means you have about 35 minutes approximately to work on the practice, which is found in your textbook on page 483. There's a whole variety of different problems for you to practice. I don't believe that in 35 minutes you'll get through all of these, but if you happen to, I'm sure there are other problems from the previous 3 lessons that you can go back and practice as well. But you should have enough to keep you busy till the end of the class. I will be back this afternoon, so if you have me for physics, I'll be around, and I will get your quizzes marked and back to you by tomorrow. I hope you have a great rest of the class, and we will talk to everybody later.